Okay, so let's try to study this problem edit distance. Okay, so the problem says that write a program that takes two strings and compute the minimum number of edits needed to convert the first string to second string. Okay, so basically two strings are given and we need to convert the first string to second string, and how many minimum number of edits needed, that we need to find out, okay, to convert the first string to second string. Okay, and the types of edits are allowed, types of edits or operations allowed, it's insert, delete or replace. So either we can insert a character, we can delete a character, or we can replace a character, but we need to find out the minimum number of edits or minimum number of operations, okay, to convert the first string to second string. Now what are the real world applications for this algorithm? So when we do spelling mistakes, few advanced editors like Word gives us the suggestions, like we call it as a autocorrect feature. So for example, over here we have written as RECIEVE, but it gives us the suggestions, the nearest meaningful word, which is RECIEVE, or received or receiver, like that. Okay. Another application is in computational biology. So this algorithm, along with other algorithms, gets used to transform one DNA to another DNA. So basically we use it in DNA sequencing. So in longest common subsequence, we that algorithm say that how common two DNAs are, but in edit distance it say that how close two DNAs are. Vladimir Levenshtein, who was a Russian scientist, had invented this algorithm. So that's why we call this algorithm as Levenshtein distance as well. Now another theory, so let's take few examples and try to understand the algorithm. Okay, so let's say we have Saturday, this is word 1, and word 2 has been given as Sundays. Okay, now so to convert this Saturday to Sundays, so what we can do, we can remove this 80. So remove 80. So how many operations? 2 operations, because we removed 80, right? So now so it becomes Saturday. Okay, Saturday. Okay, now if we replace R with N, replace R with N, then it becomes Sunday. And how many operation? 1 operation. Now we need to, it is Sunday, so we need to insert S also. So insert S. Insert S. So how many operation? 1 operation. So now it becomes Sundays. So Sundays. Okay. So total how many operations? So total 4 operations. And this we need to calculate, we need to return. So let's take another example. ACE. Now how many operations allowed? Replace, insert or delete. Okay, so we'll first try with replace. So replace T with E. So it becomes ACE. So how many operation? 1 operation. Okay. Then we'll try with insert. Okay, so we'll insert E over here. So ACT over here. Okay, so E we have inserted. Okay, so it word 2 was ACE, word 1 was ACTE. Okay, so now it's not same. It's not same. ACT is not same. So we need to remove T. So first we insert E. So this is 1 operation. Then we need to remove T. Another 1 operation. So total how many operations? 2 operations. Okay. Now we'll try with delete. Okay, so we'll delete t, so we'll delete t. Okay, so this becomes AC and what to ACE. Okay, now if we delete t, then delete t, so one operation, and insert e over here, insert e, one operation. So total how many operations? Two operations. But we need to find the minimum edit distance, right? So minimum operation, right? So what is the minimum operation? So it is the only just the replace. If we do, then we'll get the minimum operation, so which is 1 over here. So edit distance to convert ACT to ACE is 1. Okay. Now one thing you can see over here, so we are finding all possibilities, like all possible operations, and then we are trying to find the minimum number of operations, right? So when we are trying to find that, when you try to find that all possible operations, okay, then we try to find the minimum, then which approach comes to our mind? So basically you can think of taking recursion over here. Okay, I mean recursion is fine, but how to approach with recursion? Okay, so let's find out. Okay, so over here we can see, like if you move from left to right, so then we need to match the prefixes over here. Okay, and if we move from right to left, then we need to match the suffixes over here. Okay, and while matching the suffixes, so or prefixes, we will have two cases. So either you can see like this T and this E is not same. Over here C and C is same. So we'll have two cases over here. Okay, so cases, so either letters at current index are same, or letters at the current index are not same. Okay, so if we let's take the first case over here. So for example, we have one string ADE and ACE. Okay, and we need to convert. Okay, so this is, let's say this is word 1 index. Okay, so you are moving from right to left, and this is word 2 index. Okay, now at current index, these letters at the current index are same. So over here, if we are same, then where we'll go? So we'll move to next index. So basically word 1 index will become word 1 index minus 1, and this one will be word 2 index minus 1. So we'll be pointing over here, okay, and we can have a function, and we can pass these two parameters over here. Okay, now the second case. Okay, letters at the current index are not same. So let's say we'll take the same example over here, ACT and ACE. Currently it is pointing at word 1 index, and this is word 2 index. Again we are moving from right to left. Okay, so basically if we are thinking to replace, so again the case, the letters at the current index are not same. Okay, so then we'll have three options like replace, insert, or delete. Okay, let's take replace first. Okay, so over here if we are thinking to replace T with E, so basically if T has been processed and E has been processed, and T has been processed, then where will go? So this word 1 index will be pointing over here, and word 2 index will be pointing over here. Okay, so in that case we can say word f of word 1 index minus 1 and word 2 index minus 1. Okay, so this is for replace. Okay, let's check insert. Okay, so over here let's take the same example ACT and ACE. Okay, now we are thinking, okay, now over here this is word 1 index, this is word 2 index. Okay, word 2 index. Okay, and we are putting E over here, so this becomes ACTE. Okay, now when we are putting E, over here, then basically this E has been processed. Then basically we can move to the next index, which is word 2 index -1. Okay, and word 1 index will remain same because we are not changing anything over here. Okay, so this becomes insert case. Okay, now let's check the delete case over here. Okay, let's take the same example ACTE and ACE. So this is word 1 and this is word 2. Okay, this is word 1, this is word 2, and over here this is word 1 index and this is word 2 index. Okay, now we are saying like, okay, we'll be deleting T over here. Okay, we are getting rid of T over here. Okay, so what in that case over here, so it earlier our word 1 was pointing over here, right? So in that case word 1 will be pointing over here, so in that case it will be word 1 index -1 and word 2 index will remain same because he is not doing anything. Okay, word 2 index will remain same. Okay, so let's have a function over here f, and we'll have 2 parameters, word 1 index, word 1 index and word 2 index. Okay, and we will be calling this function with f of mn, where m is the length of s1 or word 1, n is the length of s2. Okay, okay, so let's check the base cases over here. So let's say word 2 is empty. So we had ACT and ACE. Now ACE is empty. Then what we need to do? We need to remove all characters from ACT. Okay, so in that case, how many operations? 3 operations. So in this case over here, so if we can say, so rather than checking the string, we can say like if word 2 index is equal to 0, then we can simply say return word 1 index. We can write, so basically whatever word 1 index is pointing over here, so to remove all the characters we will have 3 operations. Okay, so return word 1 index. Similarly, if word 1 is empty, so in that case word 1 index is equal to 0, then in that case what we need to do? We need to insert all the characters of ACE. So in that case we can simply return word 2 index, because we need to insert all the characters into word 1. Okay, so that will, if the length is 3, so if the word 2 index is pointing over here, then we need to insert all 3 characters in word 1, then word 1 will become word 2. Okay, so base cases are done. Okay, so base cases are done. Okay, now let's take a variable over here, mean operation. We can say mean operation equal to 0. So we have not done any operation over here. Okay, so now we'll check 2 cases. So either letters at the current index are same, this one, and the next is 3. The letters at the current index are not same. Okay, so in that case we can say if s1 var1 index minus 1 is equal to why minus 1, because we are calling with mn, we are utilizing the complete length over here. Okay, so in that case we need to s1 var2 index minus 1, and if it is same with s2 or var2, so var2 index minus 1. Okay, then where we are going, we are moving to next index. So we are moving to next index. So you can store as mean operation as f of var1 index minus 1 var2 index minus 1. Okay, so this is first case is done. So this is case 1. Okay, else, so this is first case is done over here. So this is over here. Okay, so this is done. Else, okay, else what we'll do, so we'll do three operations. Okay, replace ops, then insert ops, and delete ops. Okay, replace ops, what we are doing, we are moving to next index simply. So f of var1 index minus 1 var2 index minus 1. Insert ops, what we are doing, insert, we are doing var1 index and var2 index minus 1. So insert is equal to f of var1 index comma var2 index minus 1. Delete ops, in this case we are moving to next index, var1 index minus 1 over here, we already done it. Delete over here, we are moving to next index, we are moving to next index, right? So in this case var1 index minus 1 and var2 index will remain same. Okay, and once we have done it, all three operations, then what we need to do, we need to do a minimum of these three. Okay, so like we have done over here. Okay, so in our example over here, we have done over here, right? So after we did all the operations, okay, it's two operation, and finally we calculated minimum. Okay, so this is one operation. So now what we'll do over here, so mean operation, mean operation is equal to minimum of replace ops, insert ops, and delete ops. And this current operation we can treat as one. So we have done one operation over here, and this mean operation, whatever variable we have declared over here, so that we can return. So this function will return mean operation. Okay, so function ends. Okay, now what will be the time complexity for this? So time complexity, so every case when these letters at the current index are not same, so we have three choices to make, right? So in that case time complexity would be 3 to the power m, and space complexity would be auxiliary stack space, so which is O of m. So this is O of 3 to the power m, and space complexity will be having the auxiliary stack space will be still be using, so O of m. Okay, but we can see over here the time complexity is exponential over here. So is it acceptable? No. Okay, so in that case we need to optimize the solution. So if we draw the recursion tree over here, so we'll see like we'll have overlapping subproblems. Okay, we'll have overlapping subproblems, and in case of overlapping subproblems, what algorithms comes to our mind. So basically we can think of taking dynamic programming. Okay, so first we can solve with memoization, okay, which is top down, larger to smaller, and another is tabulation, okay, which is called bottom up, smaller to larger problems. Okay, so I'll not write the complete code over here. So to see the complete code and the optimization part, please refer my next lecture. Okay.